Okay, so let's try an actual example of solving for the pH of a salt solution. So we're going to use that same KF that was in the previous video. So we're going to visualize this. Remember, the K comes off as K plus, it floats around and does nothing just like it does in KOH. The F minus is going to act as a weak base. So that's how we're going to write our equation. F minus will dissolve in water. It's going to act as a weak base because it's the conjugate base of HF, and this will form HF and OH minus. So this is a base, so we'd expect the pH to be somewhere above 7, which it will be, hopefully. And essentially we're going to do the ice method. So our initial concentration is 0.325. This is zeros. We're going to ignore water like always. This is going to decrease by some amount. This is going to increase by some amount. Okay, so this is our concentration of base. We need to check our assumption. The problem is we don't have, this is a base, we don't have Kb, but we can get it. There's an equation for this. It turns out that for any conjugate acid base pair, Ka times Kb is equal to Kw, which is equal to 1.0 times 10 to the negative 14th. So the conjugate acid here is, so HF has a Ka of 6.6 times 10 to the negative 4. That is not the Ka value for F minus, because F minus is a base. So we need to solve for Kb. So we would basically divide Ka over, so Kb is going to be equal to Kw divided by Ka. We have both of those numbers. Kw is a constant, it's the dissociation constant of water. And Ka is 6.6 times 10 to the negative 14th. All right, so we gotta plug that in. Sorry. So 1.0 e to the minus 14th divided by, oh, that is 14 instead of 4, divided by 6.6 e to the minus 4. And we get 1.52, we'll do a couple extra sig figs here. Kb is 1.515 times 10 to the negative 11th. Okay. Now we can check our assumption because we know the concentration of our base and we know the Kb. So again, if our assumption is bigger, if the division of these two things is bigger than 100, we don't have to use the quadratic. So 0.325 divided by 1.515 times 10 to the negative 11th. I have a sneaking suspicion it's going to be a huge number, but that's okay. Yeah, it's like, 20 billion. So definitely bigger than 100. So what that means for us is no quadratic. Okay. So in terms of doing this calculation, the rest of this should look really, really familiar. We do need to use Kb, not Ka, because this is a base. Okay. So Kb is equal to concentration of HF times concentration of OH minus, it's products over reactants, divided by F minus, and we're going to ignore water because it's a liquid. Okay, but we have all these numbers. Kb is 1.515 times 10 to the negative 11th. For equilibrium, both of these are x's, so that's x squared. And because this assumption works, we can get rid of this minus x, and this just becomes 0.325. So x is equal to we're going to multiply this to the other side and then take the square root. And we'll see what we get. So, square root of 0.325 times 1.515 e to the minus 11th. And I got 2.22 times 10 to the negative 6th. Okay, and that is X, which is our concentration of OH minus, so that's molarity. And because is our concentration of OH minus, we need to solve for POH. So POH is equal to the negative log of 2.22 times 10 to the negative 6th, and we'll see what we get. And I just plugged in the whole thing with all the decimals. I got 5.65. That is our POH. To get pH, we're going to take 14 minus that. So 14 minus our answer. I got 8.35 basically. So this is this was a weak acid, and we're starting with what we're considering to be its conjugate base, which means this is a pretty weak base. And so basically, this is above 7, but not by much. This is a pretty weak base, but it is still definitely acting as a base. Thanks.